Today, let's design an online chess platform. Two players see the clock reach 0. One player also sends a move at almost the same instant. Which event wins? And more importantly, which server gets to decide? That tiny race contains the hardest part of this design. Matchmaking matters, reconnects matter, scale matters. But if two servers can create two different histories for one game, the whole platform stops being trustworthy. So our core principle will be simple. Every game has one authoritative timeline for moves and time. We will build the system around that principle, then see how it survives retries, disconnects, machine failures, and 10 times more traffic. This is an illustrative interview design, not a description of OpenAI's production systems. Let's begin with the player journey. A signed-in player joins one matchmaking queue. The system finds one compatible opponent. Both players receive one game assignment. Then, each player connects to the same live session, submits moves, watches the clock, and reconnects if the network drops. For our baseline, imagine 20,000 concurrent games and 500 queue joins per second. A compatible player should usually get a match within 5 seconds. During a healthy regional session, a legal move should be acknowledged within 250 milliseconds at the 95th percentile. Those numbers are useful, but correctness comes first. A player can have at most one active queue entry and one active game assignment. A game has exactly one authority at a time. A move can change the board only once at the expected turn and board version. And once a terminal result is committed, no late move can revive the game. We will support matchmaking, live play, clocks, reconnects, and durable results. Chess engines, anti-cheat, chat, spectators, tournaments, and payments stay outside this design. A clean boundary is part of a good interview answer. The most useful data model follows the state transitions. A queue entry stores the player, region, rating, join time, and one of 4 states: waiting, claimed, matched, or canceled. A match assignment connects 2 queue entries to exactly one game. A game stores the current position version, whose turn it is, both remaining clock values, the active deadline, the result, and an authority epoch. Each accepted move has a move ID, an expected position version, and the version it produced. The move ID makes client retries safe. The expected version detects stale clients. The accepted version gives every observer one ordering. Finally, a session route tells a client which game host currently owns the session. It includes the host, a lease, and the authority epoch. The epoch is a fencing token. If an old host wakes up after a failover, its smaller epoch prevents it from writing a competing history. Notice what is missing. We do not persist a clock tick every second. We persist enough information to derive the clock from a deadline. That one choice removes a huge stream of unnecessary writes. Now, let's match players. The API receives a join request with an idempotency key. That key means a retry returns the same queue entry instead of creating a duplicate. The durable queue store keeps the source of truth. Beside it, an ordered candidate index groups waiting players by region and course rating band, then sorts them by join time. A matcher looks near a player's rating first. As that player waits longer, the acceptable rating band gradually widens. The index is only for discovery. It may be a little stale, so it cannot be trusted to decide the winner. After the matcher proposes Alice and Bob, one transaction checks that both entries are still waiting, claims both, creates one match assignment and one game, then marks both entries matched. If Alice presses cancel at exactly the same time, the same conditional state transition settles the race. Cancellation wins, and she leaves the queue, or matching wins, and cancel returns the existing assignment. We never invent a vague halfway state. At this traffic level, start with a modest number of regional workers and measure queue age, candidate inventory, scan work, and transaction conflicts. Do not build a globally sharded matching fabric before the numbers require one. When one rating band becomes hot, split that band into smaller ownership ranges. Let each worker own rights for its range and search adjacent ranges for candidates. Ownership reduces contention. Adjacent search preserves match quality. At 10 times the traffic, each region can use independent partition owners backed by durable logs. A worker consumes join and cancel events in order for its partition, proposes pairs, and still commits the final pair conditionally in the durable store. This introduces a deliberate trade-off. Strict global fairness would require coordination across every partition and region. That coordination increases latency and creates a large failure domain. We prefer bounded, explainable fairness inside a region. then widen the search over time. A player may not receive the mathematically perfect global opponent, but the platform remains available and predictable. The important point is that scaling changes how we find candidates, not the correctness contract. The durable transition from waiting to matched still happens once. Now, zoom out. The client enters through an Edge API. Matchmaking owns QState and produces a game assignment. A session allocator chooses a game host. A session directory maps the game ID to that host, its lease, and its authority epoch. The game host is the only component allowed to advance the live game for its epoch. It receives moves through a per-game mailbox, validates them with deterministic chess rules, updates the board and clock together, appends the accepted event durably, and publishes a versioned update to both players. Why a mailbox? Even if 2 requests arrive on 2 network threads, the mailbox turns them into one ordered stream. That gives us a small, understandable state machine instead of locks spread across the codebase. The durable event log records accepted moves and terminal events. Periodic snapshots store the board, clock state, and last position version. The log makes the history auditable. Snapshots make recovery fast. We can compact old move events after the retention policy allows it, but the final result remains durable. An outbox connects durable database changes to asynchronous notifications. If a publish attempt fails, the outbox retries without repeating the underlying state transition. Let's follow one move. The client sends the game ID, a unique move ID, the expected position version, and the chess move. It also presents a short-lived route credential tied to the player, game, and current authority epoch. The host checks the credential, the epoch, the player, the turn, the deadline, the expected position version, and the legality of the move. Only then does it compute the next board and clock state. Suppose the host accepts move M7 at version 42, writes version 43, but the response is lost. The client retries M7. Because the move ID is already recorded, the host returns the original accepted result. It does not move the piece twice. Now, suppose a disconnected client submits a different move while still expecting version 42. The game is already at 43, so the host returns a stale version response with the latest version. The client reconnects before it tries again. The acknowledgement should follow the durability rule we choose. For this design, the host durably appends the event before acknowledging it. That costs some latency, but it means an acknowledged move survives a host crash. Within one region, a replicated log or quorum write can still fit the 250 millisecond target. Explicit outcomes matter. Accepted, replayed, stale version, wrong turn, illegal move, expired clock, or finished game. Clear contracts make both clients and operators much easier to reason about. A session route is a lease, not a permanent address. The directory says game G belongs to host H at epoch 12 until the lease expires. The host renews that lease while healthy. Every state-changing write is fenced by epoch 12. If the host fails, the allocator waits for the lease boundary, assigns a new host, and conditionally increments the epoch to 13. The new host loads the latest snapshot, replays later events, reconstructs the active deadline, and checks immediately whether that deadline already passed. The old host may recover with buffered work, but it still holds epoch 12. Storage rejects its rights. This is how we turn split brain from a timing hope into an enforceable rule. For a normal client reconnect, the player asks the directory for a fresh, short-lived route and sends the last position version it saw. If only a few moves are missing, the host returns deltas after that version. If the gap is large or compacted, it returns a snapshot followed by newer moves. Every update carries the position version, so the client can discard duplicates and detect gaps. The board animation may be optimistic, but the authoritative state always comes from the ordered server timeline. Now return to our opening question. The clock reaches 0 while a move is in flight. We need one answer, even if the timer service and the network disagree about the order. For the active player, the host stores remaining milliseconds, turn start time, and an active deadline computed with a monotonic clock. The client renders a smooth countdown locally, but that display is advisory. When a move reaches the authoritative mailbox, the host compares the trusted server receive time with the active deadline. If the move arrived before the deadline, the host subtracts elapsed time, applies the move, switches the turn, creates the opponent's new deadline, increments the position version, and persists the whole transition atomically. If the move arrived after the deadline, the same state machine commits a timeout result instead. Once that result exists, the late move returns finished game. A timer wheel or ordered deadline index wakes the host near the deadline, but the timer is only a wake-up hint. Its timeout command includes the game ID, authority epoch, expected position version, and expected deadline. The host rechecks all 4 values inside the mailbox. If a move already advanced the version, or failover changed the epoch, that timeout command becomes a harmless no-op. So we never ask whether the player's animation showed 0 first. We ask which command the one authoritative state machine accepted under the stored deadline. That is the only ordering that counts. To operate this system, watch the invariants directly. Alert on 2 active assignments for one player, conflicting session epochs, version gaps, repeated timeout transitions, and acknowledged moves missing from the durable log. For performance, measure matchmaking weight by region and rating band, queue transaction conflicts, route lookup latency, mailbox depth, durable append latency, reconnect recovery time, and timer drift. These metrics tell us which component actually needs more partitions. The services scale independently. Matchmaking partitions by region and rating ownership. Session hosts partition by game ID and can be rebalanced only at safe lease boundaries. The event store partitions by game ID, so one game's history stays ordered. Read-heavy history and profile endpoints can use separate replicas without entering the live move path. The trade-offs are intentional. We accept bounded regional fairness instead of global matching coordination. We pay for a durable right before move acknowledgement. We use server authority even when a client countdown looks smoother. Each cost protects the same property, one trustworthy timeline. If you remember only 4 ideas, remember these. Pair queue entries with one conditional transaction. Route every live game to one leaseholder with a fencing epoch. Seriphilous moves and timeouts through one per-game state machine. And derive the clock from durable deadlines instead of writing every tick. That is a design that starts simple, survives retries and failures, and has a clear path to 10 times the traffic. You can practice the complete interview problem and compare your own design with the editorial on FastPrep.